I am looking now at two different graphs, and we're going to be discussing a topic known as isomorphism. So informally, isomorphism means that the two graphs are the same. This particular figure, we'll find that these are isomorphic. But if you look at the figures, they do not look the same. So what does it mean when we say they're the same? Well, it just means that there is a way of pairing things up so that the figures look the same, even if the letters of the alphabet are not the same. So let's say we look at this figure on the left. You might notice there's a triangle here, and there's a triangle there. So I could take this triangle and sort of bend it around to the top. Then I would have maybe A, B, and I wanted to flip that triangle up, so I'll do this. A, B, C, F, D. Now there's a few other edges here. So that doesn't look quite the same as that, but it's starting to look similar. Now this one has a box. That doesn't look like a box, but actually these 4 points together sort of make a box. So I could redraw this to make them look like a box. So I have my F, C, D, and I wanted to make it look like a box, so I'll pull B down below. A gets pulled over there like this. And I'm missing a point. A has this little connection there, which I didn't label. That was E. So I need to throw that in. I'll stick it in the middle to make it kind of look like what this had. So I've gone through a process here of taking my figure and sort of evolving it until it almost looks like H. Now these have one difference. The center point is connected on different sides, so I'll just take a mirror image of this. So I'm taking the mirror image, so the D goes there and the C here. And now I've managed to take my original figure, kind of slide things around a bit, and notice I got the same answer both ways. So we say that these are isomorphic because they're actually the same figure. This G and H didn't look the same, but if I kind of bent it around a bit, I'll eventually see that things that are adjacent in G correspond to some adjacency in H. And likewise, if they're adjacent in H, they correspond to some adjacency in G. Now, in order to show things are isomorphic, intuitively, this approach of kind of bending your figures around works well. However, when we want to make this rigorous, we also need some more mathematical notation. And we'll call that an isomorphism. There are different symbols used in different books. I prefer to use a Greek letter for isomorphism because then there's no chance of it matching up with something in my figure. So the isomorphism, I will use the Greek letter phi. We'll take parts of graph G and send them to parts of graph H. And it needs to do this in such a way that if things are adjacent in G, they're adjacent in H. So that means if 2 points, let's say we call them X and Y, were in graph G, then they get sent to points that are adjacent in graph H. And this needs to be an if and only if relationship, meaning if you took something here, it better correspond to something back at the start. So we can do that mathematically by putting an F there. That means if and only if. Okay, so I need my isomorphism then. Well, my diagram will help me figure that out. For example, A was warped a few times until it got to this point. So A corresponds to S. B was moved a few times until it ended up with where U is. And we can continue this process. C ended up where R was. D ended up where Q was. E ended up where T is. And that has one letter left, F, ended up at the top where P is. So this is called an isomorphism, and it tells you how to pair up things in graph G with things in graph H in such a way that anytime there was an edge in H, there was a corresponding edge in G, and vice versa. So PQ, for example, is D and F, and notice there was DF. The other way around, say there's AE, so A and E means that S and T must be connected, and they are. So anytime that you are asked to find an isomorphism, this is the approach to take. It is okay if you don't draw that series of figures like I did. Maybe you can look at the figure and quickly figure out how to pair them up. But if you can draw the series of figures like I did, then you're much less likely to make mistakes. So let me give you an example of a mistake that many students will make. So this is a wrong answer. So many students will just look at degrees. Now, it is a fact that degrees matter. For example, E was the only thing with degree 1. So it had to pair up with T, the only thing with degree 1 there. But after that, it gets less obvious. A is degree 3. Well, over here, there are 1, 2, 3 choices of degree 3. And only one of them is correct. So E paired up with T. And then A, well, A could be any degree 3, right? So maybe I make it Q, because that's degree 3. So here's where I went wrong. That's not okay. Why? Well, looking back at our original figure, A and E are next to each other. That means in the isomorphism, they still need to be next to each other. So T is only next to S. So if I want to make this go from being wrong to right, we want it to be right, then I need to get rid of this, of the second one, and fix it. So E went to T, and A is next to it. So A must go to S. Now what comes next? A is next to 2 points. One of those points is part of a triangle. One of them is not. So I'll just take B. There's no particular reason, just might as well. So next to A, that's next to S, I look for a degree 2. There's only one choice, U. and I'll continue from there. Next to B is C. Next to U, the only option is R. Continuing on, D is next to A and C. So its image must be next to S and R. So there's S, there's R. Well, D has to be Q then. D could have been U, but the degrees are wrong. 3 and 3 works, 3 and 2 does not. And then E. U is already dealt with. In fact, I started from that because it was a case that was unique. So I'll take that away. So what's left? F. Well, F was next to C and D. They correspond to RQ. So the only thing left next to R and Q is P. Or I could have simply noticed that that's the only thing left. So again, the wrong approach to isomorphism was just look at degrees. However, that was a good starting point. So I looked again for something that was unique. There was only a single degree one. So I paired it up with the single degree one. And then I was able to build out from there. That was next to A, so that A had to pair with S. And I kept on continuing this way. I keep building out from what I know and making sure that I pair it up with the correct corresponding term on the right. So again, degrees are helpful. You have to preserve degrees, but it's not good enough to just match up 2s and match up 3s and so on.